Hello everybody. Today we will discuss representations in quantum mechanics. I will also describe postulate 3 of quantum mechanics in this video lecture. Representations in quantum mechanics are the fundamental tools because they allow us to go from the abstract ideas of state space to concrete mathematics that further allow us to solve actual quantum mechanical problems. Now, this lecture actually is at a very fundamental level of understanding of the quantum mechanical systems. Now, in this lecture, we will try to understand how to represent a quantum state or thereby a quantum system. So, we will use the representations, and these representations will be taken as fundamental tools which we can use to take any abstract ideas of state space to actual solution of the quantum mechanical problem. Now, in state space, we define representation through an orthonormal basis that spans the entire state space. Now, the question here is that what is state space and what are these representations? Now, to explain the state space, let us go into the classical world and think of the vectors in classical terms and the vector space. Like for example, you have a 2D space, two-dimensional space, and you will have two axes, x and y, let's say. Those two axes will be termed as the orthonormal bases. Using these two axes as reference, we can describe the complete planar space in the two-dimensional system. In the same way, we have state vectors which are analogous to the vectors in classical world. So therefore, state vectors in quantum world are equivalent to vectors in the classical world, and state space is just equivalent to the vector space. Now, if I say that the entire vector space is spanned by the two axes, so I can very safely say that we use the orthonormal basis in the quantum systems which will span the entire state space. Now, what are orthonormal bases? Just equivalent to the axis in the two-dimensional planar surface. We will have orthonormal bases in the quantum systems. By using the linear combination of these orthonormal bases, we can cover the entire state space. Now, like for example, if we have, in the case of a single qubit system, let's say a qubit is represented by ket psi, I can represent this qubit as alpha ket 0 plus beta ket 1. Now, in this case, ket 0 and ket 1, these are the eigenbases or the orthonormal bases for a single qubit quantum system. I will use these two orthonormal bases, and I will use a linear combination of these two orthonormal bases as alpha ket 0 plus beta ket 1, where alpha and beta are two complex numbers. I will use this linear combination and I can describe any quantum state which is represented by ket psi. Right. So this is the case of a single qubit system. In the exact way, I can use the orthonormal basis to represent any quantum state for that system. Like for example, if I use two qubits, so what will be the orthonormal basis in that case? Ket 0, 0, ket 0, 1, ket 1 0 and ket 1 1. This will be the orthonormal basis for a 2-qubit system, and I can represent any qubit by the linear combination of these orthonormal bases. Right. So let us try to expand the discussion further. Okay. Okay. So to answer this question, we start as follows. Because I was telling you that we have to start by defining a basis. So let's see how to define a basis. What we will do is we will choose a set of ket vectors in the same way as we chose a set of ket vectors in a single qubit system as ket 0 and ket 1. So for in general, for any quantum system, we will choose a set of kets, and that we represent as ket ui, which are orthonormal. So these kets are orthogonal to each other and they are normalized. That means their length is confined to unity, and the ket vectors are orthogonal to each other, and this orthonormality can be expressed using the inner product, and that will be given by the Kronecker delta ij. So Kronecker delta ij is equal to 1 when I is equal to j. So that means the length of the ket vector will be unity, and if I is not equal to j, in that case the two kets will be, the dot product between the two ket vectors will be 0. So therefore they are again orthogonal to each other. So the ket vectors satisfy the condition for orthonormality. Now this set of ket ui's form an orthonormal basis if for every ket psi belonging to the vector space there is a unique expansion. Now this set of ket vectors will form an orthonormal basis only when, if we can use this orthonormal basis to represent any ket psi in the complete vector space, or particularly for the quantum systems it will be a Hilbert space. So there is a unique expansion that exists which says that, so any ket psi we can represent it as a linear combination of the orthonormal basis vectors or the ket vectors with coefficients given by Ci's. Right. Now the question is that so this equation gives me the quantum state using the orthonormal basis and the coefficient. Now the question is that how to find out these coefficients. Now to find Ci's, what we have to do is we have to project ket psi onto basis ket uj. What does it mean is that, let's say we want to find out the coefficient for uj, one particular ket vector. So what we will do is we will project ket psi onto this ket vector, which is corresponding to the Cj. Cj is the coefficient that we are looking for. Corresponding to Cj is its ket vector, which is uj. So we will project ket psi onto ket uj. So this is done by taking the inner product. So this is basically a projection of psi onto ket uj. And if we expand ket psi, so I will get this, take out the scalar value outside, and this will be equal to the Kronecker delta. So if again, as I just mentioned you, delta ij is equal to 1 when I is equal to j. So when I is equal to j, so therefore this whole summation term will give me the value of Cj. So that is the coefficient value for ket vector uj. So this is how we can calculate the expansion coefficients by projecting quantum state onto these basis states. Now we call Ci's the set of coefficients. Now this is what is the topic of the lecture today. So we call these coefficients the set of coefficients Ci's as the representation of ket psi in the ket ui basis. I hope you understand now the meaning of every small term that I'm using. Now, let us discuss about the eigenvalues and the eigenstates in the quantum mechanics. So we have operators in quantum mechanics. Operators are the basically the functions which are performed on the quantum gates or the quantum states. So the operators are mathematical objects that allow us to represent physical observables in quantum mechanics. So there are two terms, operators and observables. The operators which are measurable will be called as the observables. Right. So when we measure a certain property of the quantum system, that will be termed as the observable. So when we measure a physical observable, this is very important. So when we try, see, before measurement, the quantum system is in quantum superposition state. When we do the measurement, so the quantum state collapses. That means the superposition collapses to a particular state. Now, which state it will collapse to? The only possible outcome of the measurement is one of the eigenvalues of the associated operator. That means that the property which we are trying to measure, basically it is a matrix, it will have the eigenvalues, it will have the corresponding eigenvectors. Now when we measure the physical observable, the only possible outcome of the measurement will be one of the eigenvalues, right? And the quantum system will be in one of the eigenstates corresponding to that eigenvalue. So that's a very important principle of quantum mechanics, and that basically forms what we call as the postulate 3. The result of the measurement of a physical quantity is one of the eigenvalues of the associated observable, right? Which eigenvalue? The postulate does not state that. It only states that it will collapse to one of the eigenvalues. That's postulate number 3. Postulate 4 and 5 will talk little bit about which eigenstate. Even then, in postulate 4 and 5, the measurement will be probabilistic. It is not exactly telling us which eigenvalue it will be taking after measurement. So it will be giving us the probability distribution that the quantum state will collapse to a particular quantum state with this probability distribution. So we will see once we come to postulate 4 and 5, and we will discuss thereon. Now consider the action of the operator. So let us consider an operator A, and let us consider the action of operator A on ket psi, such that the only way in which operator A changes ket psi is by scaling it with a constant. With this operator A acting on ket psi, we are expecting the operator will change the quantum state ket psi in a way that it is just scaled. So which is equal to lambda ket psi. So lambda is the scaling factor. Basically, this is the eigenvalue equation where lambda is the eigenvalue of A operator and ket psi is the eigenstate or the eigenvector corresponding to this eigenvalue. Now this equation is called the eigenvalue equation of the operator A. The eigenvectors of an operator. Now what are eigenvectors? And because we will talk about the eigenvalues and eigenvectors a lot in this course. So what are eigenvectors basically? The eigenvectors of an operator are the special directions in the vector space for which the operator does not change. So eigenvectors actually describe the special directions in the vector space. So along these directions, the operator does not change value. And this set of eigenvalues, so operator will have a certain set of eigenvalues. This set of eigenvalues is called the spectrum of A, spectrum of that operator. Thus the eigenvalue equation is quite often written as because this equation is different from this equation. See here, this is operator A acting on ket psi is equal to lambda ket psi. We are writing here A acting on lambda, this eigenvector. So basically only difference between this equation and this equation is that we have replaced ket psi with ket lambda. Why? Because we are treating ket psi as the eigenstate. So that is why often we can write the eigenvalue equation as the operator, the eigenstate, the eigenvalue and the eigenvector. So this is the eigenvalue, this is again the eigenvalue equation. Now one very important concept in quantum mechanics is there, which is known as the projection operators. So we will cover this projection operators in this video lecture only, because it is also related to the representations of the quantum states. Now consider a quantum state ket psi which is normalized. How do we say that? Because the inner product is 1. The projection operator projects one state to the other quantum state. So it projects one state to the other quantum state. So this is a very important point to be considered, because there are many situations which can result into a change of quantum state from one state to the other. So there are in fact many situations in quantum mechanics where this type of projection is necessary. When we measure the property of a quantum particle, quantum mechanics tells us that the state of the particle collapses into a different state. So at the time of measurement, the state may collapse, and we will use in that case the projectors, or the projection operator allows us to mathematically describe this collapse, because before the collapse the quantum state is different, after the collapse the quantum state is different. We can use the projection operator to explain the quantum collapse in mathematical terms. Now projection operator associated with ket psi is denoted as P cap in the subscript it is psi, and is defined as the outer product of psi with itself. Right. So this is the projection operator. Now let us consider the action of this projection operator on an arbitrary state. So how do we explain this? Projection operator acting on ket phi. So if we substitute the value of this projection operator, this is outer product and this is ket phi. So if we solve this will come out to be the quantum state ket psi just scaled by a scalar. So C is a scalar here, it can be complex number, and this is so the role of the projection operator on a certain state ket phi is to change the quantum system into another quantum state, just scaled version. Just you can say that the projection operator associated with psi acts on ket phi and gives another ket which is proportional to psi. So it gives us another ket which is proportional to only psi, because there is C quantity, so it is a proportionality constant. The proportionality constant is given. Actually, what is the value of this proportionality constant? It describes the overlap between the initial state phi and the state psi that defines the projection operator. So the projection operator describes the projection of one state onto the other, right? So this is how the projection operator can be used to find out the overlap between the two quantum states. Now there are certain properties of the eigenvalues and the eigenvectors. We can just describe these properties also. So we know that this is the action of the operator A onto ket psi. This is the eigenvalue equation basically. So if we construct a new ket with alpha ket psi, with the scaled version of the initial ket psi, and if we apply the operator on ket psi dash, so we get another eigenvalue equation which is given by operator A acting on ket psi dash, but this is equal to lambda into ket psi dash. So the new state is ket psi dash, but the important point to remember here is that the eigenvalue remains the same, right? So this is the eigenvalue equation that we get, and it tells us that any multiple of ket psi is also an eigenstate of A with same eigenvalue. An eigenvalue is telling us about a direction in the state space. Any state along that direction, whatever its length, is an eigenstate of the same operator. So that eigenstate, basically eigenvalue, is telling us about a direction in the state space. So along that state, different states, the eigenvalue will remain the same, is an eigenvalue. So the length of that direction, to remove this freedom, so there is a degree of freedom available to us which says that along that direction the eigenvalue will remain the same, but we have to limit that degree of freedom. That means we have to limit the length of the direction, length of the vector. So we will work always in terms of the normalized eigenstates. So we will choose alpha. So this alpha we will choose in such a way so that the dot product, the inner product of ket psi is equal to 1. So that means that explains the logic for the normalized eigenstates, because along that direction, which is represented by the eigenvalue, which is represented by the eigenstates, right, the eigenvalue remains the same. So we have to limit that length. So since state space is a complex vector space, a term called the global state will come in. So this further explains there is a term which is global phase. So if we change the state of like for example here, if we change the state of the quantum system so that there is a multiplication of the global phase with the initial state, so ultimately we know that ket psi dash is also an eigen, because ket psi dash is also an eigenstate with same eigenvalue. So if this is the case, then the new state is also normalized, right? So this gives but there is a point to be considered here. The global phase will not have any effect on the quantum in terms of quantum mechanics, right? Why? Because when we take the inner product here, the global phase term just cancels out. Now we can also describe the projection on the eigenstate. So consider state psi and an observable O with eigenstates as ket psi. So what we have to consider here is that we have to consider a projector on eigenstate AI is given. So projector on AI is given by this projection operator. Now this operator projects any state onto the spanned by onto the space spanned by AI. Alright. So let me try to explain this using an example. So let us say if you have a ket psi, you have a quantum state ket psi which is given by alpha ket 0 and beta ket 1. We want a projector onto ket psi. That means we want to project ket psi onto ket 0. Right. So we want a projection of ket psi on ket 0. How can we do it? We will take the projection operator of ket 0, which is given by the outer product of 0. So therefore we apply this projector on ket psi. This is just the explanation of what we have previously described about the projection operators. So now we have the projection operator available with us for the ket 0 state. Now we apply this projection operator onto the new state on the quantum state ket psi. So we perform a little bit. So this is the outer product. This is the matrix obtained using if you solve the outer product, and you apply this projection operator on ket psi, and you get the alpha ket 0. So that means the projection onto ket 0 you will get if you if you apply the projection operator for 0 onto ket psi, you will get the overlap of ket psi with ket 0. So that part you will get with this projection operator application on ket psi. With this application of projector operator on ket psi, you will come to know the ket 0 component in ket psi, which is basically alpha. So similarly, we can project this ket plus state onto ket 1, right? So this is just the explanation of that. Now there are certain properties of the projection operators which we have to always remember. The projection operators are idempotent, means it squares itself. If you take the square of the projection operator, it is the projection operator itself. And the projection operator is Hermitian. If you take the adjoint of the projection operator, it will come out to be equal to the projection operator itself. And if you take the adjoint of an outer product between the two quantum states, it reverses the order. So if we take ket psi, if you take the outer product between psi and phi and you take the adjoint, the order will be reversed. You will get the ket of phi and the bra of psi. Earlier it was ket of psi and bra of phi. Thank you very much for this.